So you have probably read in your textbooks that when you heat up a conductor, its conductivity decreases. Instead of increasing, it decreases. While for a semiconductor, the opposite happens, that its conductivity increases. Well, for semiconductors, it's very clear why that happens, because electrons get excited and they basically jump to the higher energy levels, thus becoming free electrons, and then they can transfer the charge. So yes, heating semiconductors will increase its conductivity. But what about conductors? So for conductors, you have to look at the Drude model first of all. So what it says is that the drift velocity of electrons, that is the average uh, velocity of the electrons in the direction of the field, right? And by average I mean the average of the vector velocity, not things like the RMS speed, or yeah, not the average speed, the average velocity. So that drift velocity is given by the acceleration that the electron experiences while it is moving, times uh, the average time for which an electron moves, because it will move for an average amount of time and then it will collide with something, and then it will lose all the memory that it had, all the information about the velocity it had, and then it will go on doing random motion. So if you think of it as a bunch of electrons doing the same thing, so they will first of all be doing random motion and they are moving, right? They're not stopping yet, so they will be getting accelerated, and then after some point, after on average this tau amount of time, they will hit with some particles, and then those bunch of electrons, they will once again start doing random motion. So the net effect of all of this happening is that the net drift velocity of these electrons, that thing is that acceleration that they experience while they are moving, times the average time for which they move. Now the acceleration, when there's an electric field acting on these electrons, that's straightforward to calculate. That's just E by m times this field, and the field is of course just delta V upon L. Now that times tau, that's what the drift velocity is. But we don't want the drift velocity, instead we want the current through the conductor. So the current is given by the area through which the electrons are going to pass to conduct the current, times the number density of electrons, that's the number of electrons per unit volume, times the drift velocity. So as we increase the temperature, there will be more random motion, which is because of the increased velocities, and thus the collision frequency of these electrons will also increase, which means that this tau, this will become smaller. What that means is that they will be having less time to get acted on by the acceleration. So their drift velocity, that will decrease as well. So the drift velocity is acceleration times tau. Tau decreases, so drift velocity decreases, and from that we can say that the current decreases. And that's why when you increase the temperature, the electrons can't conduct as well. So basically they don't drift as well. That's nice. And just for completeness, I'm also going to tell you about the band diagrams of conductors. So for a general conductor, you have this kind of molecular orbital. So uh, all of the anti-bonding orbitals, they will combine to form this conductive band, and all of the bonding molecular orbitals which are filled with electrons, those will form the valence band. And as you can see, the valence band and the conductive band, they are very close. So essentially there's no energy gap between these two. So even a small amount of field can make electrons jump from here to here, and once they are in the conductive band, they can conduct. All right. So this is what metallic bonding looks like. You can see that there isn't much stabilization because of these molecular orbitals. It would be pretty much the same if there were no molecular orbitals and instead it was just all atomic orbitals. There is some stabilization but not that significant. Now let's look at something like covalent bonding or ionic bonding or something like that. So let's look at a semiconductor which has covalent bonds. So this guy's band diagram looks like this. So all the highest occupied molecular orbitals, those have the electrons in it completely filled. So this band is completely filled, which is the valence band in this case, and the conduction band is empty as always. That's how it should be. So this homo thing, it could be anything, but generally it's the bonding molecular orbitals. Similarly, this LUMO thing, it could be I don't know, orbitals from the next period or higher orbitals, any higher orbital, not just the anti-bonding orbitals. It could be anything, but in general you have anti-bonding molecular orbitals which form this band. So notice there's a little energy gap between these two bands, and that makes the electrons that makes it harder for these electrons to jump over here. So a little bit of potential difference, little bit of field, it won't do it. It won't bring these electrons from here to here directly, well, at least not a lot of them, and we want a lot of them. So what we can do is just heat them up, right? Just heat up the semiconductor. That will increase the energy of these electrons, and then they will basically go into the higher orbitals. So if you heat this semiconductor, some electrons go to the conductive band and then they can conduct. So heating up semiconductors increases its conductivity. You can also do something else which permanently increases its conductivity, which would be to dope this semiconductor. And by doping I mean injecting some other kind of atoms, so atoms with one more or one less electron than the thing that the semiconductor is made of. So if you inject atoms which have an extra electron, then that will be n doping, and you will be creating free electrons in the conductive band. And the reverse would be p doping, which would create holes, which are basically fake positive free particles. Actually they are fake because there's no such thing, right? That's obvious. So why do we even consider these things if they are fake? Because it makes us easier to visualize how the process of conduction is actually happening. So let's just think about like this. You have these atoms, and if we are talking about silicon, then these would be having 4 electrons, right? There would be some bonding with unknown atoms. We can't see them, that's why I'm calling them unknown, right? So that's good and all, but now what would happen if I inject some atoms which have an extra electron? Well, no, in this case we want atoms which don't have an extra electron. So say, look at this guy doesn't have an electron over here, so there's a vacancy. What other electrons can do is jump into this vacancy and basically eliminate this vacancy. So this jumping into that will create a vacancy over here. So you can think of it as if this hole, this this is not okay, this hole, this actually jumped over here. Basically what happened is that this electron jumped over here, but you can think of it as a fake hole particle that jumped forward like that, and then this hole would jump to some other place, say like this, and it keeps on going. So that's why we consider these holes as particles, even though they are not. Yeah, so that happens with n doping and p doping. You can permanently make these good conductors. And then there are insulators which have like a really big energy gap. So in this forbidden zone, no electron can enter, and since it's so big, no electron can jump to here even after we heat it up for a good temperature. It still doesn't work, and that would be insulators. Now there are ways to conduct electricity through insulators, right? If you create a really big potential difference, like what happens with natural lightning, then that would conduct electricity through insulators as well. But just us, that's not so easy to do. Yeah, with the technology that we have, we can make small sparks. You have seen Tesla coils on YouTube and stuff. But yeah, like, we call them insulators for a reason, right? Because they insulate, they don't allow electricity to pass through them. So that's it. Yeah, I'll see you guys in the next video.